Ojoti, orbital velocity. Say it, orbital velocity. Again, orbital velocity. So what the means of orbital velocity? Find this one. But this is the initial velocity required to place a planet, an artificial satellite into its desired orbit to revolve what it is, and the means of orbital. So orbital velocity is come from the word orbit. Okay? If you have any question, don't hesitate yourself to ask it in the comment section. Okay. So before I define the orbital velocity, I would like first of all to define the terminology that we heard it several times. I've been mentioning it several times, and this terminology we call it the orbit. What's the orbit? So orbit is a specific path taken by the planet or satellite to revolve around the heavy body in the universe. Write it. I won't write. This is dictation. Write it. If you can pause, you can repeat this video in order to get this definition. Orbit, what is orbit? Because I want to know if you are listening or you're just playing the videos. Orbit is a specific path. What is orbit? Orbit is a specific path taken by the planet or satellite to revolve around the heavy body in the universe. Finally, let me repeat for the last time. Orbit is a specific path taken by the planet or satellite to revolve around the heavy body in the universe. I believe that you got it and you enjoy it. So now let us come to the word orbital velocity. So this is the velocity which is required to be given to the satellites to orbit around them. So we have the term orbital velocity. Orbital velocity. So the question is, what is orbital velocity? What is orbital velocity? So we say that orbital velocity we say that orbital velocity is the initial velocity required. This is the initial velocity required. Initial velocity required by the satellite. Okay, initial velocity required by the satellite to orbit the Earth or the planet in the specific orbit. That's how we define the orbital velocity. What is orbital velocity? This is the initial velocity. Okay, required by what? By the satellites to do what? To orbit what? The planet in the specific orbit. So what does provide the initial velocity in the space there, or maybe outside the Earth's surface? Then the source of the initial velocity is a rocket, the total rocket propulsion. Make sure that you go through the concept of rocket propulsion, Newton's law, in this YouTube channel, because there's a lot of things that we have learned and exciting for A-level students to understand them. Okay, so that is meanings of 40 orbital velocity. So now we like to do the derivations of 40, the general orbital velocity, derivations of this orbital velocity, yes, and then computing its value. Yeah, the subject is still interesting. Okay, so now I want to take you to another concept which we call the derivation. Derivations of 40 of this orbital velocity, because It is initial, so it's common for all the, or it's common, not common actually, that there are, yes, it's common. We say that's common. Is it common? Yes, there's a constant value of this orbital velocity. Right? In case that we said that when the satellite orbits very close to the Earth's surface, there is a definite initial orbital velocity. Okay? If the satellite revolving the Earth in a very close orbit to the Earth, then the orbital velocity will be known. Derivations of orbital of the formula, not of the orbital, derivation of the formula derivation of the formula of finding the orbital velocity. The orbital velocity. Right? So let us learn how we can derive this orbital velocity, or the formula for the orbital velocity, or for finding what the orbital velocity. So we say that consider the planet, not the satellite, of mass ms that orbit the S at the orbit of height h from what? The Earth's surface. So this is the first step of our derivation. So you need to have a sketch that circular orbit, so that consider a satellite. Consider a satellite of mass ms revolving around the Earth at the height of h from the Earth's surface. One, determine its initial velocity that we call orbital velocity. So it means that the second step, let us sketch the orbit of what? Of the satellite. Okay? So we say that this is the Earth's surface. Right? Suppose the Earth is a circular, and then this is the orbit of the planet, orbit of the satellite, of the natural satellite. They say it is communication satellite. I like them because they are providing information, which is a very important piece in human life. So this is the Earth. Okay? So this is the Earth. We say that, yeah, we have the two centers. Yes, this is the center of the Earth. Right? So this is the Earth's surface. Follow along this figure, Earth's surface. And then here, this is, suppose that here we have mass of the Earth. Or we say that not at this point, the best way, or the best point is this point. This is mass of the Earth. So mass of the Earth, and here we do have radius of the Earth, RE, from here, from the Earth's surface to the center of the Earth. Remember, this is the center, we call it O, so it's a center. Again, this is the height. So this is the height where the satellite has been placed. So for clarity, this is the height, and this height is measured from the Earth's surface. So this is the Earth's surface. This is the planet orbit, no, satellite orbit, and then this is the head H. This is the head H. So what is this? This is satellite sorting orbit. Again, suppose that here we have again the mass of the satellite. The mass of the satellite, this is S. Right? So what's happening there? According to the Newton universal gravitational law, we say that the force of attraction, there's the force of attraction between the satellite and the S. Because these are the two bodies which are in the universe, and this force of attractions between them is very proportional to the product of the year masses and inversely proportional to the square of the mean distance between the year centers, right? So that's the concept. So here we have force of attraction. Suppose that the mass of the S is here. So here we have mass of 40 of attraction. The S is attracting, or the S is being attracted by the satellite, and also the satellite is being attracted by the S. So that's the second step. So the third step, we say that recall, or we have to recall the Newton's universal law, or Newton's universal gravitation law. Newton's universal gravitational law. So according to this law, we say that the force of attractions between the S and the satellite will be given as universal gravitational constant G multiplied by the mass of the S multiplied by the mass of the satellite, and then this is inversely proportional to the mean distance, or to the radius, which you call the R square, usual. This is according to Newton's. So right now we say that in this case, this radius is equal to H plus radius of the S. You agree? Okay. So then we say that the force of attraction for this case is equal to gravitational constant times mass of the S, mass of the satellite, over the square of the radius, and this is equal to the gravitational constant, mass of the S, mass of the satellite, then the radius of the S is the height or radius of the S, called the RE. RE means R of subscript of E plus what? Plus height, and this is squared. Right? So this is first equation. Why do we consider this? Because the distance from the center of the S, when that suppose that maybe the clear notations is like this, that may do minor correction, excuse me. This is the mass of the S now. Okay, so here we have the S, and here we have 40%. So for this case, the satellite is attracting the S, and also the S is attracting the satellite. So now the distance between these two bodies is radius of the S from here to here plus the height where we place the satellite on the S, from the S surface from here to here. Right? So that's the first equation. So because our desire, we need to find the orbital velocity. Then, in case of gravitation, I told you in previous lectures, especially that in lecture 3 and lecture 4, or in session 3, session 4, even in session 2, I touched a little bit about that. I told you since the session 2, session 3, session 4, I told you about centripetal force. And this centripetal force is always acting toward the center. So the satellite, the natural satellite, the artificial satellite, is the one that providing the centripetal force towards the S. So that's the third step. So the steady state, we say that, recall the formula of 40 centripetal force, and this we call TFC, centripetal force. So from the concept, or from the previous lecture, we say that the centripetal force is mass of the body, for example, of the satellite, multiplied by the velocity of the satellite square, which is velocity of the satellite, SAVS, over the radius square, radius of the satellite, right? So, but we say that, but for that case, from the figure below, the figure above, we say that, or figure in the previous column, we said radius of the satellite, means from the center of the S to the satellite is equal to the radius of the S plus the height where we place the satellite. So if that the case, you say that the centripetal force is equal to the mass of the satellite, velocity of the satellite, which is equal to orbital velocity of the satellite, then you have radius of the S plus the height. Right? At the case. So suppose that this is the second equation. So if that the second equation, we say that the second equation, if that the second equation, say that that is fine. If that the second equation, then we say that according to Newton's universal gravitational law, right? He said that for the satellite to remain in its orbit, then the force of attractions between the satellite and the S should be equal to the centripetal force provided by the satellite. Right? So this is the third equation per se. So we can equate now. We say that mass of the satellite times gravitational constant, mass of the S, then radius of the S, plus height, where we place the satellite square. This is equal to what? Mass of the satellite multiplied by the orbital velocity of the satellites divided by radius of the S plus the height where we place the satellite from the S's surface. So with this now we can simplify the mass of the satellite. We reduce one sum of radius of the S and the height, and then we get to the gravitational constant. Then we have multiplied by the mass of the S divided by what? Radius of the S plus what? Plus height. And then this is equal to what? Velocity of the satellite square divided, velocity of the satellite. So that's the orbital velocity. So it means that let Vs to be equal to be orbital velocity. To be orbital velocity. So then we say that the orbital velocity now, Vs, will be equal to the square root of what? Of gravitational constant times mass of the S over radius of the S, which is constant, plus height of the S, that which we don't know. So this will be the first formula for orbital velocity. Have you enjoyed? If you didn't understand, you can review this video as well as you can several times. So you can replay back. You can watch several times as well as you can for you to understand and grasp. And in case that you forgot, don't worry. We physicists, we don't claim the formulas. There's a lot of formulas, hundreds formulas in physics, so we cannot claim all of the formulas. we just remember where should we start and the steps that to follow to reach our destination. So this is the first formula of orbital velocity. So it means that now maybe clearly orbital velocity, to clarify this concept, orbital velocity of the planet, of the satellite, excuse me, this is equal to universal gravitational constant times mass of the S, and divided by radius of the S plus the height of the S. Okay? Again, we can simplify further because, Newton has given us a lot on this concept of gravitation. Okay? So again, we say that also from the concept of the weight of the satellite to orbit the S, the weight of the satellite should be equal. So that force of attraction is doing a lot because it should be balanced. There's a greater force and also should balance the weight of the satellite. Should be equal to that, to the force of attraction. The force of what? Of attraction. The force of attraction between what? Between the satellite. Between the satellite and what? And the S. Between the satellite and the S. Okay? So that's a concept that I want to share with you. Okay, so what does it say? So weight of the satellite should be equal to the force of attraction. Right? So this is going to be the first or the fifth equation. The fifth equation, because the fourth equation is this one. Suppose that this is the fourth equation. So then what the weight of the satellite? Mass of the satellite times gravity. So what the attraction, force of attractions? It was equation 1, equation 2, equation 1. It was equation 1, which I told you that mass of the satellite times universal gravitational constant times mass of the S, then multiplied divided by what? Radius of the S plus height of the S, and this is squared. Right? So then mass of the satellites and mass of the satellite will cancel. So what remains there? Gravity. So gravity times this one. So make these products the subject. So if you make that the subject, you have gravitational constant, radius of the S plus height square. This is equal to gravitational constant, mass of the S, and this is the sixth equation. Why did we deduce this sixth equation? We want to determine the orbital velocity in case that the orbit of the satellites is closer or is the closest to the Earth's surface in such the way that the height from the Earth's surface to the orbit of the planet is negligible. That's our interest. But that's the focus of Sir Isaac Newton. Okay, so it means that from these six equations, you find that it's closely related with the fourth equation. So it means that we can take the fourth equation. I think that because we've been following some steps, we say that according to the Newton universal, this was the fourth step. Okay, fourth step of the derivation. Then now this is the fifth step. So I want to take you to the sixth step. So the sixth step, we want to substitute equation 6 into equation 4. That's the sixth step. So the sixth step, we have to substitute equation 6 into equation 4. Right? So we say that orbital velocity, Vs square, is equal to what? Is equal to now G radius of the S plus height square plus what? Plus h square. And then this one, we divide it with what? Radius of the s plus h. Right? Fantastic. So now we can simplify this and one of them. So you find that the orbital velocity is equal to gravitational constant inverse now. This is acceleration due to the gravity, and then times what? Radius of the s. This is it. Oh, I made a mistake. Excuse me, please. Let me correct this mistake. In case you are considering the weight of the weight of the satellites, or the weight of the satellites on the Earth's surface, then this height where the satellite is should not be taken into consideration. So here we have radius of the s square, only that. So even here we have radius of the s square. So do that minor corrections, and then even here we don't have this kind of expression. We do have what? We do have, instead of GME, we don't have universal gravitational constant, mass of the s. Then there we have what? Radius of the s plus h. So this one replaced with GRE always, and then divided by what? The radius of the s plus what? Plus h. So then orbital velocity for this case will be equal to square root of what? Of g, radius of the s square, then divided by what? Radius of the s plus h. I would like to insist you something important. You have to bear it in for the rest of your life. And this concept that is important, which you have to bear it for the rest of your life, is the constant, or the relationship between universal gravitational constant, mass of the s, radius of the s, and the universal gravitational constant. So note this. In gravitations, you have to remember that universal gravitational constant times mass of the s, this is always to acceleration due to the gravity, and then radius of the s square. So bear this in your mind, please. Right? Because if you know, there's no need for you to derive, but I have derived it to remind you, in case that you forgot in the previous lecture. So he said that our orbital velocity right now is equal to the square root of what? Square root of g radius of the s square divided by what? Radius of the s plus h. So because this is the square root, then if you square, you find the square root of radius of the s, then we find that this is equal to the radius of the s, and then you have square root of what? Of acceleration gravity, and then we have again the square root of what? Radius of the s, sum of radius of the s, and what? And the height where we place the planet. So again we say that the orbital velocity, the formula for orbital velocity, also it might be given by this one. Square root of acceleration gravity, radius of the s, plus height h. So also this is the formula for orbital velocity. Then here we have radius of the s outside the square root. Okay? So if that's the case now, in case that we know, or in case that when the satellite is always in across the surface in the orbit, very close to the Earth's surface, whereby, so now we can say that so we say that the determination, not derivation now, we use that formula, determination of orbital velocity of the satellite orbits near to the S. When we say that near to the S, it means that its height is negligible. We say that if the satellite is orbiting or revolving, is orbiting what? Is orbiting the S in such a way that the height from the orbit of the satellite there, the height is very small, very small, such that radius of the S plus the S from the plus the height of the satellite is very small. So this is approximately equal to the radius of the S. So what does it mean? For example, if you find that the satellite is revolving the S in 100, let's say, kilometers, so that is negligible because it's near the S's surface, right? So if negligible, it means that we say the sum of the radius of the S and height where we place the planet is approximately equal to the radius of the S, right? So from this case now we say that from the formula of orbital velocity, which is equal to the radius of the S, then you have square root of gravitational constant, radius of the S plus height, but this height now is negligible. Then we say that orbital velocity is equal to the radius of the S, which is constant, and then we say that this is gravitational constant, and then this one is radius of the S, like this. So this will make what? So if you simplify, you inject, means you apply the radius of the S inside the square, hence you'll find that this is GRE square, and hence divided by what is RE. So RE and RE will cancel. So it remains what? So it means orbital velocity right now is equal to the square root of gravitational constant times radius of the S. Not gravitational constant, excuse me. That is acceleration to gravity. Don't worry, sometimes you can make correction. It means that you can ignore how I wrongly pronounce some of the terms. Just take considerations of the rotation, right? Don't think that this acceleration gravity today we can change it and call it universal gravitational constant. No, the universal gravitational constant is the capital G, right? So in case that maybe you had sometimes that I confuse these two notations, you have to remember that it's just a human error, which I'm trying my level best to minimize it. So the orbital velocity now, the initial velocity required for that satellite, it will be the square root of what? This is 9.8 meter per second square. Okay, and then you have radius of the S, which is 6.4 exponent 6 meter, right? So the orbital velocity for this case is equal to what? Just to find the product for units, don't worry. So if you multiply these two quantities, you'll find that it is 7,919, 7,919.596 meter per second. So orbital velocity, this we can approximate, is equal to what? In physics we approximate that this is equal to 8,000, right? This is equal to 8,000 meter per second, right? So therefore, the orbital velocity, in case that will be asked, then you have to follow all the steps that I told you to derive the formula, and then you determine it. It's not tough. I simplified. Can you imagine if you learning yourself. You load the books, the physics books, you summarize, you get the concept. Maybe this concept from Melcom, this is from Roger, this is from Understanding Physics, this is from University Physics. You take another concept from Charlie 1, you see, and hence you combine them, and hence you'll be trying your level better.